Hi, my name is Shubham Maurya and I'm a Masters of Science Computer Science student, and I would like to welcome you to this video lecture on Gaussian Mixture Model for course COM 6915 Machine Learning. In the world of machine learning, we often deal with unlabeled data, meaning data without predefined categories. So today we will explore how GMMs can help us to uncover the hidden patterns and group these data into meaningful clusters. So, for the agenda for this video lecture, we're going to proceed in this manner. First, we're going to introduce the GMM, then we're going to talk about his assumptions, then we're going to learn about his algorithm, and we're going to compare that algorithm with other available algorithms. Then we're going to talk about hyperparameters, which can help us to control the output of the GMM, and then we're going to talk about its limitations, and then we're going to understand how we can use GMM in our real life, and we can build tools with everything, and then we're going to conclude our findings. So let's talk about what is GMM. So GMM is a probabilistic approach for the to clustering. For example, let's take an example. Like imagine bunch of data points scattered around like a bag of colorful candies. So GMM approach this data with with the specific belief that the data points likely come from mixture of several Gaussian distributions. So those familiar with like bell-shaped curves, each Gaussian distribution represent a cluster, and the data points closer to a particular curves are more likely to belong to that cluster. This use a probabilistic approach, which is its key strength. And unlike some clustering methods, GMM allow data points to partially belong to multiple clusters, which reflects the uncertainty in the real world data. For example, let's take an example here. You see there are three clusters of three different colors: blue, cyan, and green. On the left hand side, you see there's a data point which is marked with a red circle here. So the probability of that point belonging to the blue cluster is 1, right? And its probability belonging to the green or cyan is 0. Whereas on your right hand side, you see there's a cluster which reflect the uncertainty in the real world, right? It shows like that a data point is belonging to the multiple clusters, so the probability of it belonging to the blue cluster is 0.2, while the probability of it belonging to the cyan is 0.8. Like how data is available in the real world. So GMM allow us to do this. GMM allow us to represent the data like how we represent how data is represented in the real world. Now let's talk about its assumptions. So there are like few assumptions GMMs make about the data. First, the data should be continuous, like height, weight, or purchase amount, and the GMMs wouldn't work well with data like favorite color, like which is categorical data. And the second type, the second point is GMM assume each cluster follows a Gaussian distribution. This means the data within a cluster tends to be clustered around a central point, with values gradually decreasing as we move away. Finally, GMM assume the cluster are independent of each other. Now talk about this algorithm. So GMM relies on a very clever algorithm called expectation and maximization. For this video tutorial, we're going to use EM for short, and it's a very iterative process that works in two steps. First of all is E step, which is like expectation step. In this step, the algorithm assign each data point to a cluster based on the current estimate of the Gaussian distribution. It's likely making an educated guess about which candy bag each candy belongs to. So this is called E step. Here is the formula for the calculating the probability, and calculating the distribution. Then the M step. which we call like maximization step. Once the assignment are made, the algorithm refines the Gaussian distribution themselves. It adjusts the mean and variance of each Gaussian to better fit the data point assigned to it. Imagine using the guesses from the expectation step to improve the candy bags themselves. Now, so this EM algorithm keeps repeating these expectation and maximization step or E step or M step until it converges, meaning the cluster and the Gaussian distribution stabilize itself. Now, let's talk about relationship to the other ML approaches. Hey, uh, you might be familiar with the another clustering method called K-means. Both K-means and GMMs are unsupervised learning techniques, but there are key difference. K-means assign each data point to a single cluster definitively, like sorting candies into separate bags. GMMs, on the other hand, allow for softer assignment, reflecting the possibility that a candy might fit into multiple bags to some degree. Another advantage of GMMs is that they can automatically learn the number of clusters from data. With K-means, you need to predefine the number of clusters, which can be tricky. But with GMMs use its technique like Silhouette analysis to find the optimal number of clusters for the data. So it automatically clusters the data based on the its behavior. Now, let's talk about the hyperparameters of the GMM. While EM algorithm learns the parameter of the Gaussian distribution like mean and variance, there are some settings as a user we can control, and these settings we call like hyperparameters. One crucial hyperparameter is the number of clusters, like which we discussed earlier. Choosing the right number is important to avoid underfitting and to or overfitting. So another hyperparameter is the covariance type. So this control the shape of the Gaussian distribution. They can be uh, spherical or diagonal, tied, full, and these choice depend on the characteristics of our data. For example, like if we're using full conversion, so it allows more flexibility in the shape of the Gaussian cluster, but this is suitable uh, for example, if we have a customer segment customer segmentation program, so how it's going to like it's going to suspect the like different buying patterns. If you are trying to find the different buying pattern, then full conversions is very useful for us. But if we are centered around the specific buying behavior of a customer, then we would go with the spherical approach. So these are the different covariance types. Now let's talk about its limitations. So the GMMs are very powerful tool, but they do have limitations. As mentioned, they work best with the continuous data, height, weight, right? And they can struggle with the non-continuous data like text category, and additionally GMs are sensitive to initial placement of the Gaussian distribution. Different starting position can even lead to slightly different results. So these are the limitations, and there is like GMM assumes that the clusters are Gaussian shaped by default, and if our data cluster have more complex shape, then GMMs might not be the ideal choice for us. Now let's talk about sample applications. It can work as a anomaly detection, image segmentation, speech and handwriting recognition. Let's take a like full-fledged example like customer segmentation, as I talked earlier, right? GMM is going to use its method to cluster the customers on its purchasing behavior. For example, like purchasing frequency or the amount they spend. Then GM will to train model automatically to cluster those patterns, and then we can use that the data produced by the GMM for our marketing campaign, like how we can approach like different customer different in different ways. We can make future plans for the role. In conclusion, GMMs are very probabilistic clustering method which use Gaussians. It has soft assignment learning curves, we can learn more by extending our knowledge to HMMs. So these are the things, and these are my references which I used for this presentation. I would like to thank you for being part of this video lecture. Thank you.